Last class, what we discussed was orbital reference frames, right? And the different frames we have discussed until now, the first one was perifocal reference frame, also called the PQW. Then we discussed the geocentric right Ascension and declination frame. This is very similar to lat long, okay, latitude and longitude. And then we discussed the geocentric, was it the equatorial frame? Geocentric equatorial frame. Right. This is also called ECI frame. Okay, I may use the term ECI frame sometimes. Don't be confused or don't be overwhelmed as to trying to figure out what this frame is. Okay, ECI frame is nothing but just geocentric equatorial frame, and ECI stands for Earth-centered inertial. Okay, it's essentially Earth-centered and it's inertial, which means it is not rotating with Earth. Okay, it is going around the sun, but it is not rotating along with Earth. There is a similar frame called ECF or ECEF frame. Okay, this ECF or ECEF, it stands for Earth-centered and fixed. This is a non-inertial or Earth-centered, Earth-fixed. Okay, this is a non-inertial. It rotates along with Earth. The ECF and ECI frames align at the on the day of vernal equinox. These two frames align, or every 24 hours, these two frames align once. So this frame is rotating along the Earth. This is useful if you're practically, this is more useful. It's easy to imagine through this frame, okay, because you're rotating along with Earth, so you know this frame is constant, so you can define everything, and given a particular time and date, you will know what is the conversion between this frame and this frame. Okay. So the next important segue, which this leads us into, is orbital elements. All right. This This is by far the most important information you should know as orbital engineers or as space engineers. Okay, if you, let's say you go into grad school or you take up a job as a space engineer, specifically as a space engineer, people expect you to know this like the back of your head. Okay. Practically speaking, when you're having a conversation as a space systems engineer or a space engineer, you're going to be talking a lot about orbital elements, the different aspects of a satellite, the communication, how it orients, what orbit it is in. All that is embedded in this orbital elements. So what we are going to do is, I'm going to refer you to a 3D visualization, and then I'm going to explain what these orbital elements are. Okay. All right, can you see this? Do you want me to, is it visible or you want it to be blown up? It's visible. Let me try to blow it up a little. Better? I think this is, seems like this is the optimum size. Okay. You don't have to take a picture of this. You can, this is on, I'll send you this link so that you guys can refer this. Okay. Looking at this, first, can you identify, you see Earth over there? Do you see the equator or equatorial plane? Which is the equatorial plane? Right. The rectangle is the equatorial plane, or it just cuts to the equator. Do you see the orbital plane? Right. The green thing which circles around, that is the orbital plane. Now if I ask you to identify the perifocal reference frame, can you tell me what the perifocal reference frame is? It will be in the orbital plane, but what is the reference PQ? Can you tell me the P, Q and W direction? Say that again. Right, exactly. So H is the W direction, right? So what is the P? You're right. H is pointing in the W direction. What is the P direction? That is RA. Right. Correct. So you see, this is the P direction. You're right. Okay. So P direction. This is the sorry. This is not the P direction. This is the P direction. You see the perigee. We talked about periapsis. Periapsis and perigee or perigee mean the same thing. Periapsis is a generic term for the closest point of approach for an orbit, and perigee is specific to Earth. If Earth is a central body, your periapsis is also referred to as perigee. Understood? It's in an orbit, the shortest distance is the perigee or periapsis. If Earth is the central body, your periapsis is called perigee. If Sun is the central body, what is it called? The general term is periapsis, regardless of what central body it is. But if for Earth specifically, it's called perigee. G comes from GO. If it is Sun at the central body, it's called perihelion. Make sense? So helio comes from Sun. Okay. So this is the P direction. You see it? What is the true anomaly here? Can you identify? You know where the satellite is. Do you see where the satellite is? Huh? The orbiting body or the satellite? You see it, right? So what is the true anomaly? We discussed true anomaly quite a bit. Theta. This angle between the perigee and the satellite position, that is the true anomaly. Okay? So your P and W are these directions. The perpendicular to P in the orbital plane. You see, H is not in the orbital plane, right? H is perpendicular to the orbital plane. The perpendicular to P direction in the orbital plane is Q direction. Get it? So Q would be something like this, going in the orbital plane, going like this. Okay? So that would be your Q direction. That would be your perifocal reference frame, PQW frame. Any doubt in that regard? Okay. So let's look at the geocentric equatorial frame. Do you see the geocentric equatorial frame here? So geocentric you do see it, right? What is the do you see the X direction? The vernal equinox, right? See, this is the vernal equinox, the X direction, right? And do you see the Z direction? So the two directions which you define are the X and Z direction. For perifocal frame, we define P and W. Q completes the triad. Similarly, for the geocentric equatorial frame, we define X and Z. Z is essentially perpendicular to the equator, or it's the axis of rotation, and Y completes the triad. The triad, right-handed triad. Okay. If this, so this x, y, z is the inertial frame. It does not rotate with Earth. Okay. It's a frame which stays there. This frame would just rotate with Earth. Got it? So at one point you align on the first day of spring, you align the ECI and ECF frame. ECF rotates as Earth goes around Sun. The ECI just stays there. It always points to the vernal equinox. ECF does not always point to vernal equinox. You understand the difference? Now let's look at orbital elements. The first one you're going to see is A. Do you see A? What could A here be? What did we say A was? The first orbital element there is A. What was A? Do you remember what A is? It's the semi-major axis, right? So semi-major axis defines the size of the orbit. Can you see this? Can you visualize A here? Can you visualize A? What is A? Here you actually, it's difficult to visualize A, okay? Because see, if you're looking at, so this is your perifocal frame, okay? So we said A, this is F, okay, and this is F star, right? See, here we are visualizing Earth as just a dot. What is A? A is this length. The semi-major axis. Okay, this is your orbit. The problem with this is, the reason you cannot visualize A here is, we cannot really say the orbit is circular here. It could be ellipse. If it is elliptical, you don't know where the center is. Okay, what is this point if for an elliptical orbit? That is the focus, that is the occupied focus, that is not the center. Okay, that is this point. Right? So you cannot really see this center. And A is the distance from center to the periapsis. This is a semi-major axis. All right. The second one, semi-major axis defines the size of an orbit. The second one is E. E is called the eccentricity, and it defines the shape of an orbit. So you guys are already aware that E defines the shape of an orbit, right? If E is 0, what is the shape of the orbit? Circle. If E is between 0 and 1, it's an elliptical orbit. If E is 1, it's a parabolic orbit. E greater than 1, hyperbolic orbit. So you see, E defines the shape of the orbit, right? The shape, depending on what value E is, the orbit changes. And this is, see, typically this E is the vector E. Okay? Here vectors are used with when we define our vectors, we use this notation, right? In here, this is the notation being used, okay? So this is a eccentricity vector. Eccentricity vector points in the periaster's direction, always, okay? But eccentricity defines the shape of an orbit. All right, so these are the first two sets, or the first set, size and shape of an orbit. Okay. The second set defines the orientation. So we'll see one at a time. The first one is I. Do you see the angle I here? Do you see angle I? Right. Angle I defines the inclination of an orbit. Inclination of an orbit with the orbital plane, the ecliptic plane and the orbital plane, the angle between them, or the angle between the perpendiculars which define these planes. You can either take the angle between two planes, or you can take the angle between the perpendiculars, right? It's the same thing. You agree? So this angle, you can see this plane, the inclination of this plane with respect to this plane. Or you can say the angle between this vector, which defines this plane, and this vector z, which defines this plane. That is the inclination, how inclined it is, the orbit. The equator is always going to be the same, right? It's not going to change. Equatorial plane is not going to change, but orbit may change. So you define the inclination of an orbit with respect to the equatorial plane, or the vectors which are perpendicular to the equatorial plane. The second one is omega. This is small omega. Okay? There is small omega and there is cap omega. Do you see line of nodes? Does it mean anything? Line of nodes, does it signify anything? Why is it there and not anywhere else? Why is the line of node there? What does it signify? Does it signify anything? Come on. Look at it hard. What does it signify? Does it? Huh? The line of nodes. You see this? See, it is a line of intersection between the two planes. Just like two lines intersect at a point, two planes intersect at a line. Okay? So do you see this plane and this plane? They intersect along this line. Right? Do you see it? this plane, the orbital plane and the equatorial plane, they intersect at this line of node. So the two ecliptic plane and orbital plane, they intersect at, ecliptic plane and equatorial plane, or the orbital plane and equatorial plane intersect along this line. And the angle between this, you call this as the ascending node. Why is this direction the ascending? See, there is an ascending direction and a descending direction, okay? So this red line is the ascending direction. Why is it ascending? Correct. So it's from this point onwards, it's going towards north. You see, it's ascending, right? And if you take this line and keep going in that direction, from this point downwards, it is descending, right? You see that? So there is an ascending portion and the descending portion. So this is the ascending portion, and this angle, the angle between the line of node and the perigee direction is omega, small omega. Okay? So this angle is called argument of perigee. Okay. In what plane is this angle? Angles are 2D angles, right? It's in the orbital plane, right? So this angle is in the orbital plane. You have to keep that in mind. Okay. And it's the angle between the ascending node. This node, see this node where the orbit, actually this is that node. So the point of intersection. See, this is the orbit, right? And this line, this orbital line intersects the equatorial plane here, correct? That is the ascending node. And the same, the point on the other side, where the orbit intersects with this line of node, is the descending node. Because from that point onwards, the satellite starts descending. Make sense? So you see, this is the angle of perigee. Okay. The next one, or argument of perigee. The next one is cap omega, which is it's called right ascension of the ascending node. Okay. So this angle, you see omega, cap omega is here. the cap omega angle is defined as the angle between x direction and the ascending node. Okay. So what angle, what plane is this angle in? It is in the equatorial plane. This angle is in the equatorial plane. Okay. So this is the second set. The first set is this. Second set is this. The third one defines the position of the orbiting body. Okay. And here the position is, how have we defined the position of orbiting body? Do you remember? How did we define, what term did we use to define the position of orbiting body? What term? We used a term. You forgot already? Remember, we used true anomaly, right? True anomaly always defines the position of the orbiting body. So where is the orbiting body here? This is the satellite position is the orbiting body. The true anomaly is the angle between the perigee direction and the position of the orbiting body. Here they are using V naught, but what we are doing is we are using theta. Okay. So these are your orbital elements. Now if you want, I will send you a link to this web page. You should also take a look at, see, this is this view. Okay. Do you see A here? Can you visualize A? Huh? What is A? Can you visualize the orbiting body here, orbital plane and the equatorial plane? This whole thing is the orbit, okay? The orbital plane or the equatorial plane is just overlapping the orbital plane, this part, okay? Where is the central body? The central body is here. Okay, this is that point. This is the point we have been discussing. A is half of this semi-major axis. This is the major axis. You see why this is a major axis, right? And this would be the minor axis. Running from this point to here would be the minor axis. So half of that would be semi-minor axis. Half of this is semi-major axis. So this is what we said was A. Okay, and you can visualize angles. This is the angle cap omega. This is the small omega. The perigee direction. This is the PQW direction, right? You see this, we said, we have always said this is the P direction, right? P direction, or this is the eccentricity vector. So this would be your Q direction, and the perpendicular to this plane is the W direction. So you see the PQW here. This is the P direction. The perpendicular to this in the orbital plane is Q direction, and the one coming out of this is the W or H direction. Do you see the true anomaly? True anomaly. This is the orbiting body, okay? The angle between the perigee direction and the orbiting body. That is a true anomaly. And this is the line of nodes. Okay. With regards to orbital elements, what you are going to learn is you cannot really measure these elements in space, correct? You realize that. Can you really go there and measure these angles, right? So what you can measure from ground, you're going to use that to convert those measurements into orbital elements. It could be position, it could be velocity, okay? And given an orbit, if I give you this figure without all of this, you should be able to mark those. That is one of your exercises. That will be one of your exercises. It could be this figure, a 3D representation, or it could simply be this figure, where it is the, so this, from where are you visualizing this? Do you see from where you're visualizing this? From what point? So tell me, from where are you visualizing this? No. If you compare this and if you compare this, what is your point of view? From where are you seeing this? From the top, from almost here. Not from here, you're actually seeing it from here, from that H point. Okay? If you had seen it from here, it would look much different. You have to see it from here. Okay? So that is important. You have to be able to visualize and tell me all the angles. Now this, we have been, throughout this course, we have been discussing this R. You see this R? Our two-body problem statement was about this R. We said we can figure out a relationship between R, and then a solution to two-body problem, which was the orbit equation, was about this R. Correct? Everything is about this R. Figuring out where R is. Any questions until now? In your textbooks, this element A is replaced by H, okay, which is the specific angular momentum, right? So don't be too overwhelmed by that. It is just another, you could use H or A to figure out as one of your orbital elements. Okay, these two are related actually. So why are these two related? How are they related? You remember? How is H and A related? H square over mu is what? This is P. So go back and check your textbooks, or go back and check your notes. We have used this relationship. When we derived the orbit equation, we came up with h square over mu in the numerator. Even in your exams, this was given, right? So h square over mu is P, which is called the parameter, and this parameter is equal to A into 1 minus E square. So you see the relationship between H and A. Okay. So if you know H, you know A. If you know A, you know H. We know E, right? So from E, knowing E, you can always, mu is a constant. So knowing E, you can always calculate, you can switch between H and A. Okay? Any questions until now? Is this clear? I'll email you a copy of this. It's just if you, in fact, what you should do is, I don't have to email you guys. I always use this as the reference. So this is from NASA. What you need to do is, Google for all orbital elements, okay? And there is one of the first links which appears is this, Orbital Elements, NASA Human Spaceflight, spaceflight.nasa.gov, and this link. If you just do this, it will take you to this. And you can actually look at many other representation of the orbital elements, okay? Please pass on your attendance, please.